All right, welcome back, everybody. For those of you who have to endure one more of my face, I appreciate that you are actually doing it. So my name is Arup Nanda. I was working for a company for 14 years earlier. So just 5 months ago, I moved to Priceline.com, and I run the data services from end to end. So everything about data, that's my responsibility. Those of you probably do not know Priceline.com. We are part of Booking Holdings. So Booking.com, Agoda.com, Kayak.com, Rentalcars.com, OpenTables.com, etc. Those are our parent company, and those are our brands. And I'm pretty sure one of you probably have used that. And if you are using Expedia.com, well, please leave the room. That's a big competitor to us. So we are the second biggest travel provider in the world, online travel agency. And today I'll be talking about a few things. One is how we use data science, and particularly data engineering, which is a new emerging field. Not exactly a new emerging field, but something was neglected for a long time, and then how we use it. And second, I'll be talking about how we do machine learning, etc., to do some system development, etc. And finally, we'll talk about the tool we developed. And we plan to make it open source as well, but right now it's not. Something you can actually use on your site as well. That's the thing. So data science, this is, I think we walk along the streets of San Francisco, you will obviously hear this term at least once, machine learning. Everybody talks about machine learning and data science. But there are certain fundamental concepts missing from data science and machine learning. For example, most people talk about machine learning in terms of customer segmentation, prediction of a customer behavior, etc. And those are legitimate use cases. But that is not the only use case of machine learning. So for example, we use machine learning for machine behavior, actually machine, the systems, etc., predicting the system behavior properties. For example, if you're using Oracle, Oracle database itself, what specific parameter you have to put in the Oracle init.ora file or the P file, etc. That is something that's more of an intuitive process. Most people have done that. Well, what if you use machine learning to actually predict what Oracle database, how that will behave based on a specific parameter? That is something you can do as a machine learning as well. I'll not talk about Oracle database particularly, but I'll talk about something interesting, how we use machine learning to do something really, really important thing. So for those of you who don't know how exactly the online travel agency works, so let me just give you a very quick overview of that, how that actually works. So at the one side of it, we have the demand, which will be you as a customer. And you probably go to a website, like if you're Priceline.com, for example, or you can have affiliates. For those of you who probably do not know, AAA, American Automobile Association, you can buy rental cars and hotels and airfare as well from them. They don't actually sell those things. They actually go either white level some of the stuff. For example, we provide the system behind the scene for AAA. So if you have booked through AAA, that's actually coming to Priceline.com site, I think. So that's, we call that affiliates. And the white labels as well. Those are the people who are white level. If you go to cheapair.com, might have done that, they actually do not have anything. They partner with somebody else. In this particular case, Cheapair partners with Expedia, but that could change in the future as well. They may come to Priceline, etc. So that's something you will go as the demand gets generated. To meet the demand, we have to have a supply. So in this case, we call them providers. For example, hotels, that are real hotels, or the airlines, etc. They sell the seats and the rental cars or the days as well to us. We have something called a global distribution system, which is like a stock market of all the travel products. So for example, Marriott or Hilton, etc., they might expose what rooms and in the rates they have to this thing called global distribution system. And we, as one of the companies who do that, we can go and buy that from them and then and sell that to our customers. That's called global distribution system. And finally, the affiliates itself. So some of the affiliates could actually sell those products to us as well. So this is on this other side, is the supply part of it. So you have a demand and you have a supply. And ultimately, we have to combine that together for you to come in. And that's where we come in as technology. And that's something we provide. This is the fundamental concept of any online travel agency. And you would be surprised to probably believe this. This online travel agency, this thing, is about 19% of the entire travel population. 19% only. That means 81% are still unexplored, and they're still done through telephone. offline activity. It's very surprising, but that's the reality of it. Anyway, so we are going through that process to capture more and more of those 81%, which is not captured yet. But fundamentally, this is what it happens. So what is the problem do we face in this case? The problem we face is that we have to use bots to go out and get the data from this GDS systems, affiliate systems, etc. Nobody's going to go through the stock market, let's say, to find out what the price of the stock is. You have to have a system to go and grab it and then present it to your own customers. That's what, those are the bots, we put it. So the bots get it. So we have a demand and a supply, but to make those available to our customers, we have to put them in our own inventory database. That's the important part of it. Now, this we think about this in database, inventory database, that actually sounds really simple, but think about it. We have 250,000 hotels. We actually sell that to customers. Multiply that by, on an average, 200 rooms per hotel. And you can buy a year in advance. So 365 days, multiply that, it becomes a pretty big number. And it becomes very difficult to put all this thing together into a single database to make it faster. And guess what? If you don't make it very fast, you will probably go away as a customer. If we don't cache them, we can always go and get that from the GDS systems, but that will take time. And if we don't get that, we won't get the accurate numbers, like the inventory available to us or not. So we have to make this cache available to us. But because you saw the staggering amount of data we have to put the cache, it becomes pretty much impossible. Like this particular data will come out to about 10 or 15 petabytes. It might not sound a lot, but in terms of actually putting all that into a consumable format becomes expensive to put that in together. So that's not possible. So what we do, well, what we have done in the past is we cache them selectively this way. Take, for example, this is one map of the world, the hotels, for example, New York, San Francisco, Los Angeles, Washington, D.C., Boston, etc. People thought these are hot pockets of the world, and therefore cache only those things. Somewhere, let's say in Orlando, probably not as much. Oh, actually, Orlando is not a good example. Bozeman, Montana, not a good example. So don't cache it. So if somebody searches for Bozeman, Montana, then go to GDS system and get it. So you assume that whoever is going to search for Bozeman, Montana will not go away from your site because you are going to get that. So it worked out well, reasonably well, but didn't work out all the time. For example, why didn't it work out all the time? So those of you may remember a few months ago, we had World Cup football in Russia. Certainly, if you look at this, this is how the number of visitors went to that part of the world, which because of our intuitive ability to cache the stuff, we didn't cache St. Petersburg, Moscow, Ekaterinburg, etc. We didn't actually do that. But suddenly, in that time period, we got a humongous amount of people coming to that part of the world, in specifically those things. So if we had cached them, we could have got a good proportion of them in our system. We didn't cache them because we simply did not think that would happen. So what do? Things like that are happening constantly all over the place. So these intuitive things are actually over the hotspots happening over there. We got to capture them. What that means, we have to look at somebody has to sit down and go through all the events happening in the future, all the possible events, and think about the caching mechanism. That is impossible. Can't do. That's not possible to go through it. So we have to have something like a smart caching. If you think about the caching, we're talking about the petabytes of information coming at us at a lightning speed. We got to figure out which of that we want to cache and which of that we have to move it out. Think of it as an Oracle buffer cache, very similar to that. So buffer cache assumes that if you have used it, so that algorithm has gone through that. But in this, only difference in this case is that it depends on usage as well. So what we thought of doing is that, well, why can't we use something like a smart caching over there? So for example, this cache is probably at one point was important. And as the events change, that area of the cache you have to do might change. And we can do that. We can probably use machine learning to use this information that we have so that dynamically you can find out what to cache and what not to cache. We could do that. Now, that is something most people do not think about because they think about customer behavior, customer predictability. Well, not necessarily. This is a system behavior, system probably as well. We could do that. So let's go to the next one here. So we got this GDS systems and the parts I get from GDS systems, and they write into MySQL database. So you might be surprised to hear MySQL. Really? We do caching in MySQL? Oh, yes, we do. Why? Because MySQL is pretty good actually in returning the values. If you know exactly what value you're getting, like just a simple value, MySQL does it very well. And because you can do the sharding across all the different node of the cluster, we could do that actually surprisingly fast and also resilient way. So what the bots do, which is not one bot, we have several bots. We go and grab this thing from GDS systems and write across all the things about thing. And all the inventory and rates data we store as blob, because that's the best way for the application to go and retrieve it, the blob. What's the problem? Do you guys use blob to do your analysis? You don't. You like in a relational format. Everybody wants a relational format. Even though they don't like to admit it, they actually like to see in a relational, like a tabular format. So what we did, what we used to do before, we had this ETL, extract, transform, and load, read everything from the MySQL databases, extract it, and put into Hadoop. Because that's where you do your analysis, your pricing history, etc. But the pricing on the MySQL side is dynamically changing. It's not there because we don't store what value was before. We don't need to. People book in advance, like for the future. So we have to store it for the future. We don't store, what is what day, 22nd? So we don't store for 21st. We expand them, we move them out of our cache. So to put that history data, we move into Hadoop. Hadoop was fine, so we put that. But the problem was that when you are reading from MySQL, it puts stress on the MySQL database itself, obviously. And it doesn't matter what database is used, you can also use Oracle, all that. If you read and write at the same time, you are going to put some stress on this. So what we did, we changed the approach a little bit. This information doesn't have to be in real time. When the bots go and grab stuff from the GDS system and everything, that can go asynchronously to the database. Because all we need to know is that, do I have the cache available? If I don't, I can go to the GDS system and grab it. But I don't have to have, it's not like a money deposit system. It's not like you deposit money and withdraw the money at the same time. So it doesn't have to be transactional. So we put something called a data pipe in between. It's based on Kafka. So the bots, instead of writing to the database directly, they're writing to the data pipe called Kafka. And then we also wrote consumers from the read from the pipe and write into the MySQL databases at the same time, parallelly, goes across everything. A little bit earlier, I talked about how we think about data and not databases. So when writing that stuff, we also wrote the consumers in such a way that we extract different data from the pipes into writing to the different MySQL databases. So those of you who know about MySQL, you know MySQL is, any of you work with MySQL right here? Okay, you think, so MySQL, that there's a something called cluster for MySQL as well. And the cluster, you can do an automatic sharding. So the MySQL cluster will automatically decide exactly what database in MySQL cluster this record goes into, which is great. But that means you're going to have a gargantuan amount of MySQL certs to satisfy your purpose. Because one node could be completely idle, one node could be completely busy. So it's something we could not afford to have. So we did our own sharding based on the data that comes in and goes across everything else. And that's something we got for the pipe, the Kafka pipes. We call that system Mississippi because that was the biggest, Mississippi, if you do not know, that's the biggest river in North America. And that also introduced commerce across America. And that's what America has become. So we call it Mississippi. So everything we do, we stopped writing into the database directly. It goes into Mississippi. And then from there, all the consumers simply extract data from there, remember that, not database, data from there, and either do some processing or store in something. So that we just left out. So once we got that part, so we had some APIs and common libraries, etc. So people started using those common APIs and libraries. Suddenly the mindset got completely different. It's now no longer SQL, no longer select from something. It's simply get the data from the pipe and do what you want to do with it. And one pipe, one such consumer, was the Hadoop system. So instead of reading the MySQL database directly, we directly read from the pipe and wrote into Hadoop. So that stopped the interference with the MySQL databases, and that improved the performance significantly. But remember that Hadoop is not the ultimate objective, because that's still we have to worry about getting the data out to Oracle as well, or some of the subsystems, so people can read that. So it has to go to Oracle. So this, we also wrote thing from directly reading from Oracle, reading from the pipe into Oracle. There was one little problem though. Not everything was required from the pipe, and not everything was available in the pipe, because the history data wasn't available in the pipe anymore. That was gone. So we had no choice but to read from the Hadoop to Oracle, which is fine. Sometimes you got to do that to actually collaborate it. And in reality, that's going to happen. You will have a store, and from their store, you can move data into different parts as well. So if you think about that, that's something we call that transformation happened. This is like if you think about this as any system, you would have multiple databases, multiple APIs, for example. They are either feeding into something else or they're reading from something else. This goes back and forth. And that was the ETL, that's the transformation we talked about. The problem was that every time you had to write a new transformation, you have to write a project plan, probably a 3-month project plan to have that completed. This was certainly not helping the business, because you have to have these things done over rapidly. And the third problem was that machine learning. Those of you who know machine learning or data science, you know that the way that it works, people write some models, they store the model somewhere else, they read that data and write a different model, and they probably store the data somewhere else, and then eventually write the data into some final database where people read it from. This has to happen constantly. They also tweak these models constantly as well, because by definition, it means experimentation. Machine learning is never a fixed science. It's not a recipe. You take it and you put that and it will produce a result. You have to constantly tweak it. But what happened in our case was that because we had to go through this entire ETL process all the time, so this experimentation simply couldn't happen. We are waiting for a 3-month project plan for every time. So guess what happened? The data scientists and the machine learning people, what they did, they wrote a model. It wasn't the perfect model, but they knew to change that model will take another 3 or 4 months or more than that sometimes. They say, you know what, I'll live with it. So we had suboptimal models. So we simply couldn't afford to have that kind of model. And that was the problem first I came in, that was the problem we had. So what we did. So I looked at the problem as how to categorize the problems. And I encourage you to think about it in your own organization as well. Many organizations have 3 kinds of data, I would say. First is signals data or external content. By signals, I mean the thing you collect from the website, etc. Extremely fast, but that's not usable. And that data you probably collect either using blobs, JSON objects, XML, whatever, not exactly usable format. So we got that part thing. And then we got a system of record. That's where you store the data which is relevant afterwards. If you're an e-commerce site, you probably have your bookings, customer, etc., because that's something very important for you to carry forward afterwards. And the third kind of data, we call the transient data, like caching, system set, etc., which is not important for you to store it, but it's very important for you to access very quickly. Without that, your system may not be able to sustain the demand from the customers. So there are 3 kinds of data. So what happens is that ultimately you have to massage all these things together and prepare the first one. I call that cleaning, anomaly detection, preparation of the data to be useful in the future as well. At this stage, you may want to combine several things to create a usable format. For example, the system of record, that may not exist. That data may be in the signals, which will be a probably HTTP format. You have to get the data from the HTTP format, decompose it, and write into a relational table for people to actually start using it. That's I call preparation. That's the first one. Then once the preparation is complete, you go to the summarization, aggregation, classification, etc. And then that is complete, then you go to the analytics and dashboards and metrics and the KPIs at this point. And then you go to, after that is complete, you go to query testing and experimentation, which is useful for machine learning. And then from there, you go to training data preparation for machine learning. And then we do simple machine learning, personalization, etc. And if you're really, really adventurous and your company is really mature in that, you do things like a deep learning. The reason I bring it up here is that many companies don't understand you have to go it from the bottom up approach. That deep learning will be completely useless and impossible to accomplish until you have a very solid and robust at the foundation itself. You can't bypass it. Most companies say, when I first came in, I said, well, we go to machine learning. Well, do we have all these things in the place? No, we don't. Well, if you don't, then you can't do machine learning. You can't do deep learning, etc. It will take a long time. So this is something is very, very important to have that. So I drew this picture, and then I also put this too, specifically the query testing, analytics, dashboards, etc. Most companies have a mature organization that actually does that. I call that analyst. Those are not data scientists. The data scientists operate on the slightly in the top level. They overlap in one with the query testing, experimentation, etc. But that's about it. And for them, what they need to do, they have to do it repeatedly. So, and of course, and they produce the results that goes into applications, which will be eventually used. So what we have to do is to create a data engineering platform which can do these things quickly and not a project plan every time. And that's something we do. So we had a need to do this thing. So this is a wish list. It has to be a repeatable code. It has to be very easy to transform. For example, if I want to change the query, I shouldn't wait for like a quarter to complete it. I should be able to do it in like a few minutes or maybe in a few hours, etc. Not because that you want to encourage them to do experimentation, etc. Quick to market. If I create a model, it has to go to the production stage in days, not months, and definitely not weeks either. Then scheduling has to be built in, because I don't want to go and schedule something else. And cron job is not exactly a great thing to do, I think is that. And here is another thing. We use Informatica, and probably that can do the scheduling as well. The problem with Informatica is that I can't have the customer monitor their own jobs. And I didn't want to be the man in the middle trying to decipher what happened in Informatica and pass it to the customer. I want the customer to go and monitor themselves exactly what the jobs are happening. And you also have to understand, analyze the past metrics. A specific job, for example, took a long time to run today. Got to find out, is it just today or have you running for a long time for quite some time so you can go and do some analysis. That's a pretty big wish list. And here's the best part of it. The way Priceline works is that our budget was fixed the year before. And I had no budget to do this. So that means I have to get everything free. So how could he do that? Well, I'm talking about 5 months ago, so I think do. So what we did, so we've settled on Apache Airflow. That is completely free product. If you haven't heard about this is actually a scheduling and a visualization product built into a single thing. So completely downloadable. It's a total freeware product from Apache. And you can install that on a simple Linux system, nothing complex required. And this is the concept behind Apache Airflow. Something you have to know as well. It's called directed acyclic graphs. If you think about it this way, you have an activity called activity 1, which feeds into 2 different activities, 2 and 4, suppose, at the same time. And both of them, after they finish, they're on activity 3. So in this, the key things to understand here is that each of these things, the green boxes, they're called nodes in the graph. And they are independent activities. They don't get something from something else, because they are independent by themselves. So they have what activity 1 completes, it may do something which will be picked up by activity 2. And only after activity 1 is complete. That's the dependency part of it. And it's also in one direction. I can't say after activity 2 is complete, run activity 1 again. Can't do that. If I do that, obviously I have to have something else in front of it. But that's why it's called acyclic. That means it doesn't go back to that. So it's directed in one direction and acyclic because of that. And it's also dependent. So if activity 4 and 2 will not start until activity 1 is complete. And one more thing also we call that idempotic. That means everything that happens inside this node has to be independent. That if you run that again with the same input, it will have the same result. So it's not going to be different. That's how they input it. So that's why that thing called DAG, directed as acyclic graphs. And that's a very important concept in data engineering. You have to keep in mind that that's going to be the key things. So this is how it looks like. I don't have access to the actual, because I don't have the VPN. This is not my laptop. I don't have VPN access. I couldn't tell you this thing. This is an actual DAG I'm going to show you from our thing. You can see that here. All these boxes, those are activities. Those are actually things. And they actually have a legend as well. Green means they're successfully completed in the last time around. If something failed, then you would show up as red. If they're running right now, you would see as a solid green, etc. So it kind of gives you an idea of how this thing is that. You can see a slightly complex graph, but you can see that here, there is no cycle back into something. There's no loop. It always goes in one direction only. That's called the DAG here. So this is that's the website of the Apache Airflow, which you call the thing. Then this is another page. If you see the top, the graph view, the tree view, the task direction, etc. Then look at this. You're looking at the tree view. Look at this one here. It shows you all the same thing, but on the right side you see the timeline, and that tells me right away. Looking at the number, like the color itself, I can tell if that particular activity failed or got successful in that time frame. And the best part is that I can grant this access to a customer without me worrying about if they can do something. We still control the schedule ourselves, but the customer can go and see that. So I'm not in the man in the middle trying to decipher what happened and trying to communicate that to the customer. They can go and get that themselves. But the best part, in my opinion, would be this one. It tells you on every day what are the different activities and how much time they took. Look at that one. On October 19th, around that time, all the activities jumped up. And that tells me something must have happened that time. So if they complained that time, I could get that as well. Then next one is the Gantt chart that shows you. It shows you very clearly how much time was spent in each of these activities. So your overall total duration will be from the time you started all the way to the end of it. But if you want to find out exactly how much time was spent within each activity, they can go and get that in themselves as well, which helps us do some troubleshooting and debugging as well. Guess what? In this case, the last two are probably taking the longest time. If I want to reduce the overall time, there's no point working on that FCI offer session tmp.s_stg. No point doing that, because that's a very small activity period. So this gives me the ability to focus, if I have to, on specific things. And this is something the customer can see as well. I don't have to decipher that the customer. So all these things are great. Then what do I need to do to make it happen? And that's the best part of it. Apache Airflow has a Python built-in scripts. This is how, by the way, this is a very long Python script. I couldn't show that thing. This one, the Python script, how it looks like. And this is, so for those of you who don't know Python, don't worry too much about it, because this is not something you'll be writing every day. Now that's the problem. Our customers, data scientists and all things, some of them know Python, some of them don't know Python. In fact, the DBAs, data engineers also, they don't know Python either. And we can't spend time in writing this long, seemingly daunting task of writing the script like this way. But that's where we had to put a thinking gaps. If you think about that, most of the stuff is actually static, boilerplate. Only few things are not. For example, the source, the destination, and the transformation do in between. For example, look at this one. It is a SQL script. Then things like an email to be sent out, to who to send out, what is the duration, etc. That is something that's all fixed. So what we did, we put a system like this. We asked people to supply us the source, the destination, and the SQL script that goes in between. And because Apache Airflow requires Python, and Python comes with something you might have heard about it, called Flask, which is the web server or the application server that's kind of built into the system. We got Flask, and we simply had a simple web page where these three things has to be supplied by them. We got that. We simply created a shell script to plug it in all the places. At the very end of it, we create this Python script repeatedly. And then we put that in the DAG. That's it. We call the system Zipline. By doing so, anybody can simply create this thing. Of course, it will come to us for approval, because you have to see that thing and make sure that it's done. But it takes a few hours to actually complete that process. And it's a few hours because somebody has to go and actually visualize that. But technically, you can just go and actually plug that in as well. And that takes about a few minutes. That is, we call that zip line, a price line, zip line, because you're moving data from point A to point B, all kinds of stuff. We did that. And when we did that, that's where the zip line sits. So all these activities, from all the way to the cleaning, anomaly detection, all the things, zip line takes care of all the activities. Of course, when the system stabilizes that, most of the stuff will be spent in that training data preparation, query testing, or simple ML, etc. Will be mostly focused on that, but it's just one tool to rule them all, and not overall. That was a very, very impressive feat for the team to actually go and did that. So just to give you an idea what happened after we put that in the place, data engineering used to take about 1 quarter to complete the process, because everything there's a project plan. It became 1 week. That's it, I think. So we can do multiple things without doing too much about it. The machine learning experiments used to take once a month experiment. Because guess what? Every time it's a big project, a lot of people have been involved in the process. We did 1 a day. And in fact, we plan it to like multiple times a day also for the machine learning experiments. The customers didn't have any visibility in the past, because Informatica did not provide all that. We had to have Informatica admin to get the information and send to the customer, and there was always offline activity. In this case, the customer exactly saw what was going on. And not only what has happened in the last time we ran, also in the past, all the wrong things. They got that as well, the picture I showed you before. And the debugging became very easy, because if I see something took a long time, I can go back and find out what exactly happened in that time frame. The one more thing I didn't show it here, over up top, it's a log file as well. If you click on that, it will show you clearly what happened in that particular node in the graph to actually show you that as well. So in this thing, just to summarize the thing, what about machine learning is something has been thrown around a lot nowadays, but it's not just for customer data or shopping data or something, the data in the business. It is also very, very useful for doing system level programming. We just saw that before. Like for example, in our case, getting the cache. The cache cannot accommodate everything in the entire world. So you have to be very smart about how much data you have to cache. But that you can't just do by some human trying to figure out what data will be relevant in the future. That's not possible. So we have to have a system built up in machine learning to figure out that if a demand goes up, then you cache that faster. But not just any demand that goes up. You have to figure out some rules, for example, like in the football thing we talked about here. The football thing was very useful. It's not just demand going up. You see the demand is going up significantly in certain markets only. So something must be happening there. When the hurricane hit in the Florida Panhandle, you would see people are leaving that area. So in that case, demand is coming down. So without a human being being involved in the picture, the system automatically reduces the price to capture more, and so on and so forth. So that's something the machine learning has been. Think always about not in terms of data base, always think about data. So how is that different? Think about the data. You don't have to have some application writing into a database all the time. Doesn't have to be. In our case, when the bots go and search for inventory and the rates and all that from outside, that information doesn't have to come to the database right away. Put that in the pipe and then grab from the pipe later on asynchronously and write into the MySQL database. So all databases you have. That's something. If you write it to the database directly, you need a massive cluster just to process the information in the first place. You don't have to, because if you put that in the pipe. So think in terms of data and not databases itself. Then similarly, think in terms of pipe and not ETL. Think about that. You don't have to go through one database, then collect something from here, transform something from there, and go to a different database. Don't have to do that. Simply get from the pipe, do the transformation in the pipe itself. I talked about a little bit about that earlier, called KSQL, called Kafka SQL, that can transform even the streaming data using SQL-like syntax. So you can extract directly from there. So for example, how many people have signed up for their specific say promotion going on? You don't have to store a raw data in the database first and do a group by operation. You don't need to do that. You can do that directly on the pipe itself. And you can move the count information into the database. So you don't have to go through every raw data in the first place. And data engineering is the foundation of data science. If you don't have a good and solid foundation on data engineering, data science is not going to be very useful. But is that difficult to implement? No, not necessarily. You saw that here. So the entire thing I talked about today is actually implemented in the last 5 months. So it's not a big, difficult task to actually do that. Yeah, granted, you're still going through perfection, is going through that, but we are in production. We are running this in production, and we are creating stuff that goes into the online, and that's been working awesome in the last 5 months. And you can use Airflow to automate and quicken the data engineering processes. And the Python code sounds like a daunting task in itself. No, it doesn't. Most of the Python code, about 90% of it, is actually static. So you can create a shell script, which will simply supply that thing is not static, it's dynamic, to create the Python code. In that case, nobody has to learn Python. And everybody, I'm pretty sure, knows how to write a shell script. That's not that difficult to do. Or if you're not comfortable doing that, whatever language you want to do, at the end, you can create the Python script easily, which will be used by Airflow to automate this process. So that's my message about thing with that. And thank you very much for the time. I know that I'm a little bit early, so I'm going to stick around a little bit if you have any questions on this. And we plan to make it open source at some point in time so that you can also download and use it to your advantage if you have to. Any questions?